I'm Joachim Breitner from Dfinity, and I'm going to show to you how responses from the Internet Computer are certified. In this talk, I'm going to explain to you how you, as a user interacting with the Internet Computer, can trust the responses that you get from the Internet Computer. So answering the question, are you really talking to the Internet Computer when you think you are? And let's start with how it would look like in an idealized world. So let's imagine you're interacting with a service that's running completely in a trusted environment, let's say your own computer or your company's network. And for the purpose of this talk, the service we're looking at might be a booking agency for show tickets. So you interact with that service and you ask it to book a ticket for you, and it will respond with, yep, you got a ticket for that show, and your seat is 5A. And as long as all the moving parts here, the service, the network is trusted, that's all you need. You know you have really booked a ticket to seat 5A. Now, making this a little bit more realistic, probably you are talking to a service over the internet. And the internet is a big, dangerous place full of malicious parties. And now you have a problem. What if somebody between you and the service you're talking to wants to mess with that request and that response? It could try to let you believe that you actually got a different seat than the one you got, which would be embarrassing when you're fighting about it with somebody else about seat 7D. Or maybe it could pretend that you actually didn't book the ticket, so you don't go to the show, and at the end of the month you see you've been charged for it. Or the other way around. It could pretend that you actually got the ticket, but then you actually haven't booked the ticket, and now you go to the show and they don't even let you in. So that's the kind of problem we want to address here. Now, on the internet, the solution is kind of known, and it's based on public key cryptography. So here what we could have is that the service has a secret key. This is the blue key on the right. And when it responds to your request, it signs that response using that cryptographic key. And this is this blue ribbon on the slides. As a user, for some reason and somehow, which is out of scope for this example right now, you know the corresponding public key of that service. So this is this little picture of the key on the slide. And using that public key, you can verify the signature on the response, and you can check, yes, indeed. The response comes from that service, and I can trust that response, and I know that I really have booked the ticket, and really my seat is 5A. So this is the conventional thing you have every day when you use some service over the classical internet. When it comes to the Internet Computer, things are similar but slightly different. So there, the service that you're interacting with isn't a full stack service server stuff on its own with its own private keys and everything, but rather it's just code running in these canisters, this unit of computation that we run on the Internet Computer, and it doesn't do cryptography on its own. Instead, it's being executed by what we call a subnet. A subnet is a collection of multiple nodes, multiple independent services or servers that collectively run the canister that is the booking agency here. And the subnet as a whole can create a signature like the one we've seen before. And here some of the magic of the Internet Computer happens. Even though there are multiple nodes that make up the subnet, and some of them may be malicious, you can only create one of these signatures if the majority of the nodes agree on what to sign. So even if a few of them are malicious, they can't create false signatures, meaning that as the user, when you get a signed response from the Internet Computer with a valid signature from the whole subnet, you know that this is the correct response, even if some of the nodes were malicious. So these signatures, they're called threshold signatures, and you can learn more about them in the other talks in this series. What's interesting here, or what's kind of relevant, is that these signatures are somewhat expensive to create. The nodes need to collaborate, they need to communicate, they need to together create one of these threshold signatures. So it wouldn't scale to sign each individual response when we want to have multiple thousands of requests per second. So how do we solve that problem? So to solve that problem, responses aren't signed individually. We really want to use these kind of expensive signatures very resourceful. So what we do is we record all the responses, or rather all the recent responses, all the responses that are still relevant, in what I call, for the purposes of just this introduction, that a document, one document of the whole subnet that lists all the recent responses. So as you can see here, somewhere among these responses, we have noted that when Kim, our user in this example, asked the service to book a ticket on a show, that booking was successful and the seat is 5A. And there are also other responses to Larry and other users. And conceptually, what we could do is just now give this whole document, which has a signature from this threshold signature key by the subnet, and as a whole, ship it to the user, and the user can look up that, yes, indeed, I have that response in that document where I expected. Now, this wouldn't be so great because I've said that we record all the responses in this document, so it's going to be large. And moreover, Kim doesn't really have any business seeing the responses to requests made by Larry to some completely unrelated service. So what we can do here is we can redact the document and only include the portions that are relevant to Kim. And I really like this analogy of redacting a document because it fits so nicely. Because you can see the document is still the same shape and the signature in the bottom is not affected. So what I mean here is we can redact the document, remove parts that Kim shouldn't see, and the signature still stays valid. And this means that now Kim can look at this document, see, oh yes, indeed, the response to my request was you got the ticket and you are in seat 5A. And it can also check that the signature is correct. So this redaction hides stuff from Kim that Kim shouldn't see. And also, which may not work directly with analogy, it makes the document smaller. You can think of it a bit like document compression or image compression. If there are lots of things that are black, you don't need to transfer that much data. So this way we get a still sizable, not too big response to Kim that only conveys to Kim what Kim needs to know. So there's a next wrinkle we have to look at. This subnet we're talking to is called subnet 5 on the slides. And that means there is more than one subnet. And actually, part of the idea of the internet computer as being this infinitely scalable thing is that you don't just need one subnet, you can have many subnets, and you can scale out that way. But in this picture right now, Kim knows the public key corresponding to subnet 5. If we now have many subnets, it wouldn't be so great if all the users needed all the public keys of all the subnets. And we solve that the following way. The idea or the goal is that Kim really only has one public key that it needs to know in some trustworthy way in some kind of bootstrapping process. And once Kim has trust in this one public key, which is a small amount of data, that should be enough to verify all the data that's coming from the internet computer. And the way we do that is that this one public key, it's yellow in this slide, happens to be this secret key of one particular subnet, which we call the root subnet. The root subnet, it's a bit like a subnet like any other subnet. It has nodes, some of them might be malicious. It also happens to be, at least initially, to be this subnet that runs the NNS. But that's not the critical idea here. Really, the thing that makes the root subnet is that the user knows that subnet's public key. And then this root subnet, in its document, and that's the same document that also records the responses and other things that we will see later, it also has one section about listing all the subnets of the internet computer. And as you can see, it lists that there is subnet 5 on the internet computer, and it has the blue key. And now, together with the response to the user, the subnet can include a redacted copy of that document. And we call that the delegation because it's delegating trust from the root subnet to subnet 5. And now the user can look in this document and find out what is the public key of the subnet that I'm talking to, subnet 5, and it will find the blue key there. And that's how we solve the problem of the user not needing to know every subnet's public key, but rather just one single subnet's public key. So that's how we certify responses to what we call update calls. Update calls are, in a way, the default. It's a request from a user that goes to the internet computer, goes through consensus, gets included in blocks, all the fancy things that you know from the other talks, they can change the state of the service, of the canister, which is of course important for booking a show, because really you want the booking canister to record that the show has been booked. And eventually you get the response, and the response is certified, meaning the user can verify the content just in the way that I just outlined. And this is great because this whole certification thing happens completely transparently to the application code, both the application code on the canister and also the application code on the client side. But these update calls are kind of slow because they have to do all these things, go through consensus and so on. It takes 2 seconds or so. And that's why we also offer as an option to do what we call query calls. Query calls are calls to methods that don't change the state of the canister. And because they don't change the state, there's no need to put them in a deterministic order or to execute them on all the nodes that would then need the new state. A query call can be responded to by one single node, not the whole subnet. And that means they can be very fast. We're talking milliseconds now instead of seconds. But you might have noticed that there's a problem now. I've said that the subnet as a whole is trustworthy and only the subnet as a whole can do this blue signature. But a single node on the subnet could be malicious. So when that possibly malicious single node responds to your query call, how do you know that the response is correct? And the single node can't sign the response using the blue key because, well, that's the point of that threshold signature that single nodes can't sign these things. So how can you do a query call and still get an authenticated response from the internet computer? Well, it is possible, and it's possible using the feature that we call certified variables, and I'll introduce it right now. An important thing right ahead is that this now requires collaboration from the canister. To certify update calls, canister code and application developers didn't have to do anything special, it just works out of the box. To secure these query calls and use certified variables to secure them, that now requires the canister to assist. And here's how that looks like. Already when the user does the booking, note that we are now looking at the request where the user wants to book the show, the canister is recording in a special area of the system state that Kim has booked seat 5A. Basically, it's telling the system, by the way, can you please remember for me that Kim has booked seat 5A? And this is now stored separately from the canister's normal state. In fact, it's written into the same document that records all the responses that we've seen earlier. And remember that that document is, as a whole, signed by the subnet using this blue ribbon. And that helps when the query call happens. So let's say a day later, Kim wants to know, what was my seat again? I forgot. And it wants to use a query call to ask the canister, what is my seat? And query call is a very nice use case for that because just checking which seat you had, that doesn't need an update call. That works nicely with a query call. And then the canister can now ask the system for, hey, yesterday I told you something that you should remember and also sign for me. Please give me that information again. So it's getting a redacted copy, again, a redacted copy, of the document of the subnet with everything redacted but the information that the canister itself asked the system to remember Kim has seat 5A a while ago. And now the canister can include that, what we call certificate, that redacted document, in the response to Kim. And now Kim can actually check that the response from the canister, yes, you have seat 5A, is correct. Of course, this needs checking the signature, but we have existing code for that. That's the same mechanism as checking for the validity of a response to an update call. It also needs to check things like, is it not too old? Because maybe an attacker gives you a valid response, but it was valid a week ago and things have changed. So there are a few things that the user, or rather the client code on the user side, will have to check. But when they are being checked, we get that the response is correct. Now, a little complication that comes due to constraints of keeping the system simple. Now, when designing a system like the internet computer, there's always the trade-off. Do we make the system a bit more complicated and its use, let's say from a canister point of view, more convenient? Or do we just provide bare minimum features and put some of the burden on the canisters so that we can keep the system simple and therefore also secure and manageable? And in this case, a decision was made to only allow 32 bytes of storage for canisters to use the feature that I just outlined. Now, 32 bytes might be enough to say Kim has booked seat 5A, but once there's more than a few people booking seats, then that's no longer enough, obviously. But that's not our fundamental problem. And the trick we can apply here to overcome this problem is pretty much the same that we've applied just a few slides earlier when we were looking at how the subnet can use one signature for many responses. And again, we're using one of these redactable documents. So what we can do here is that the canister, when Kim books the show, stores the information that Kim has seat 5A in its own little document, and it also has other information about other people booking their seats in the show. And then it calculates a cryptographic hash of the document, this green text on the slide, which uniquely identifies the content of the document. And it's that green text that it asks the subnet to store and to certify. So when now Kim asks the service for which seat Kim has, the service can respond with the document from the subnet, which includes information, what is the green string, the green cryptographic hash. Then also a redacted copy of the canister data, which says that, yeah, really the information that you have seat 5A is correct. And also, just as before, we need this little delegation thing, which connects the blue signature to the yellow key that Kim has. And with all these things in place, we can now trace the chain of trust from the response that the user gets to the key that the user already has. So the response is seat 5A, and the user, or rather, again, code running on behalf of the user, can check that this response is included in the redacted copy of the document from the canister in the lower left corner. It can recalculate the root hash, or the cryptographic hash of that document, the green text, and check that it's included in the redacted document from the subnet. It can check the blue signature on that document and make sure that this is really signed by the corresponding key for that subnet in what we call the delegation, the redacted document from the root subnet in the lower right corner. And that document is signed using the yellow key, so the user can check the signature against the public key that the user has. And that is how we can manage to certify responses that are delivered and calculated even from possibly malicious single nodes, deliver them to the user and let the user still verify that the response is correct, using just one piece of information as the root of trust that the user needs to have in advance. So let's now look a little bit closer at these documents with this interesting property that we can redact a few lines with a black felt pen and still the signatures can be validated. And of course, these are not real documents and there's not really a black felt pen. Instead, the mechanism that we're using here is a well-known cryptographic tool called Merkle structures. And maybe just to avoid confusion, when I said redactable earlier, this was really just for analogy. This is not a redactable signature in the strict sense of redactable signatures, which is a technical term, just to avoid confusion there. Now, these are really just Merkle data structures. And this is nothing that we haven't invented. This is existing technology, but it's still rather neat. And I'd like to explain to you at a slightly lower level how these Merkle structures work and how we can use them here. So far, the analogy I used was a document that we can write stuff in, but really the next better analogy that we can use here is maybe that of a file system of your hard drive, where you have folders, and these folders have names, and then inside these folders, there are more folders, and then also files that contain data. And this is the conceptual model that I'd like to keep in mind when I talk about these trees. So they're now tree-shaped because we have folders and subfolders. And the subnet maintains one of these trees, and that's why we call it the state tree, with all kinds of information. So it has the responses to requests from users. It also has the certified data that we looked at when we wanted to certify query calls, and then a bunch of other stuff, the current time, and lots of internal data that we need to keep the internet computer running, such as cross-net messaging, as you might have seen in the other talks. So this tree is, well, tree-shaped, And in this picture, I've drawn it growing down because in computer science, trees grow down for some odd reason. And we have these rounded corner things for data in the tree. So that's where we have the certified data that the canister is stored. Or in the top left corner, we have the time when this tree has been created. And now we want to define a cryptographic hash that uniquely identifies the whole tree, including all the data, all the labels on the nodes, and its shape. As a little technical step towards that, we have to make that tree a binary tree. So as you can see, the tree is branching multiple times between a node like Canister. And it's nicer for the next steps if the tree is actually binary. So every node has one or two children. And we can easily take the n-ary branching and replace it with multiple binary branching, which are little diamonds on the slides now, to get that property. The next thing we need to do is to define how we calculate the cryptographic hash of that tree. And we can do that in a bottom-up approach. So for the leaves that have data, we can just take the hash of the data. A hash like SHA-256 might work. Then we have these labels, for example, certified data in the bottom left. And there, the hash of that subtree is a hash of that label and the hash of everything below. For the binary nodes, we do something similar. The hash of one of these binary nodes is the hash of the left and right subtree. And this way, we've now defined a rule to define a hash all the way from bottom to top. And then we have a hash at the root. And this one smallish 32 bytes number is now enough to identify the whole tree. So if we sign that hash, we can use that signature to validate everything inside the tree. So the next thing we need to do is do this redacting. So let's say we want to expose to Kim that the certified data of canister ABCDFGH happens to be that CAFFEE, or whatever's written in the lower left corner. And maybe we also want to show that the current time is the time that we have there. Then we can remove all the subtrees that are not relevant for these two pieces of information. So we only leave everything from the root to these pieces of information. So we prune the tree. And I really like the word pruning here because that's what you do in the spring when you have a garden. You prune the trees and you remove the branches you don't want. But we can't just remove them. We also have to remember the hash of that subtree that we removed. And this is the little yellow annotations on the slide. And why do we have to do that? Well, if we now give the pruned tree to the user, including all the hashes for all the places where we prune something, the user can, just as before, from bottom to top, recalculate all the hashes for the individual nodes, and therefore also for the root node. And then we can take the blue signature of that root hash, the hash of the root node, and the user can validate the signature. And that's how the user can validate a signature that signs the whole tree, even though the user doesn't have the whole tree. So this is what we use in the subnet to have this document where we can redact, but it's used in more places. For example, the root subnet, well, it's just also using a state tree, but it has additional information about which subnets exist and what their public keys are. And then in the example of the booking agency where we certify the query calls, the canister itself might have one of these Merkle structures, and it might be the same one that we've just described, to include all the information about the seats that were booked behind one little small hash that it can then plug into the system as certified data. So really, this was just a summary of how Merkle trees work. As such, it's not particularly specific to the Internet computer, but it's a very versatile tool, and we can use it for good effect in the Internet computer. So in the last slide, I want to walk you through the steps that you have to take as a canister developer, or rather an application developer on the Internet computer, if you want to get the benefit of certified data to secure your query calls. And as I said, this needs some help from the canister. So there's some amount of development you'll have to do. And really, this is the cookbook for that. So first, you have to think about the kind of queries you need to secure and think about what Merkleized data structure is the right one for that. So I've shown you the tree. And the tree is really useful for everything that's a key value lookup or that resembles a file system. If you have something more sophisticated where some data needs to be aggregated or selected, and maybe you even want verification of negative results, maybe you need something different than that. And that really depends on your application. In a simple case, and many cases are simple after all, a tree like that would work. Then you have to maintain that tree as part of your normal canister state. So this is running in the main memory of your program running on the computer. And whenever an update call comes in that changes a piece of state that needs to be reflected there, you have to update that Merkle structure. You have to recalculate the root hash that identifies all the data in that structure and write that out as the certified data of your canister to the system. This is what we've seen in the slide earlier, where the canister was putting this green hash into the system state. Then, when handling a query method, you have to, well, first of all, respond to or calculate the response for the query method. Then you have to look into your in-canister Merkle structure and redact everything that you don't need. Basically, you calculate what's sometimes called a witness that proves that the response that you're actually in the process of giving is contained in that hash that you stored earlier. You also have to ask the system to give you that certificate, that redacted document that shows that the hash that you wrote there earlier during the last update call is the one that you expect it to be. And then you ship that together to the user, the response, the redacted part of your in-canister Merkle structure, and then the thing that comes from the system that proves that the root hash is the root hash of your data structure. And then on the client code, and really this kind of thing expects that you're writing a dedicated client for your service because there are some service-specific things you have to do. Well, first you check that the thing that you got from the system certificate, is correct, the signature validates. You should check that it's actually up to date, because otherwise a malicious node could give you an old result and make you believe that something is true now that maybe was true a week ago but no longer is. Then you have to check that this is really the data for the canister you're talking to. Otherwise, an attacker could install another canister on the subnet that has similar state like yours, like a fake booking agency that has the information that you got seed 7D and construct a response based on that. So you have to check that, is this the canister that I'm actually talking to? Then you look at the application-specific data structure that you got, the redacted Merkle structure from your canister. You recalculate its root hash, as we've seen earlier on the slides, and you compare that with the hash that's in the system data. And finally, you have to check that what's in the application-specific data matches your query parameters and response. And both are important. You have to keep in mind the parameters of the query and also the response. And when you've done all these checks as part of the client code, then you can trust the response even though it came from a possibly untrustworthy node. As I said, for update calls, you don't have to worry about any of these. This is happening automatically for you. So if this is too complicated, or if maybe your queries don't fit the format that is supported by Merkle structures, you still have the option of either using, well, you can either use query calls and live with the reduced security guarantees, or you can use update calls and live with a slightly reduced performance. We are working on ways of making query calls more secure out of the box, so that even in cases where, as a developer, you didn't do anything special, you get some more guarantees and some protection against single malicious nodes, but that's still in the making. So stay tuned for that. Until then, if you want to know more about the technical details of what I just presented, you will find all that in the functional specification, which is this long technical document that we've published on the SDK side, in particular the sections about the system state tree, certification, and certified data. And if you have any questions about that, we're happy to help you on the forum. so that you can use that knowledge in the development of the services that you want to put on the Internet computer. So thank you for your attention and enjoy working with the Internet computer.